Specifically, in this lesson, we're going to take a look at how to deal with double or multiple angles, as well as when to utilize a factoring strategy to solve trig equations. First, let's talk about double or multiple angles. The general procedure to deal with these kind of trig equations is to make a substitution to remove the double or multiple angle. So for example, I've written here, if we have a double angle, we might want to make the substitution beta is equal to 2 theta. Then we're going to have a trig function that doesn't have a double angle anymore. We can solve for this reference angle using the cast rule and solve for beta the way we normally would based on our last two lessons. Now the ending here is a little bit tricky. What we first have to do is apply the periodic solution. Once we have all of the solutions, we can revert back to the original theta by either multiplying or dividing. And then if we happen to be working on an interval, we need to use our periodic solution to find all of the possibilities on that particular interval. This means if we're working on an interval, we're going to keep substituting in particular integer values of n until we go outside of that interval. So let's take a look at an example to see this procedure in action. Let's solve the equation 2 sine of 3 theta is equal to 1. The first thing we're going to do is we're going to divide both sides by 2 so that we have sine of 3 theta is equal to 1/2. Now, since sine is by itself over on the left-hand side, but the inside portion of our function is 3 theta, I want to replace that 3 theta with something else. So we're going to say let beta equal 3 theta, so that we have sine of beta is equal to 1/2. Now that we have just a single angle on the inside instead of a triple angle, we know how to solve sine of beta is equal to 1/2. We're going to set up the cast rule and determine where sine is positive. Sine is positive in the first two quadrants. So let's go ahead and draw in our right angled triangles here. And our reference angle beta is going to be inside. And sine is opposite over hypotenuse. So this implies that we have a 1 to root 3 triangle, and that our reference angle beta must be 30 degrees, or pi by 6 radians. So what we have is we have that the two values that are going to satisfy sine beta equals to 1/2 are pi by 6 radians and 6 pi by 6 minus pi by 6. So we have pi by 6 and 5 pi by 6. Now that we have the values for beta on 0 to 2 pi, we're going to create our infinite solution. Well, because sine repeats every 2 pi radians, beta could be pi over 6 plus 2n pi, or beta could be 5 pi over 6 plus 2n pi. And again here, n is any integer value. But we know that beta is equal to 3 theta, so our full solution must be 3 theta is allowed to be pi over 6 plus 2n pi, or 3 theta is allowed to be 5 pi over 6 plus 2n pi. Now that we know all solutions for 3 theta, what we're going to do is divide by 3. Dividing our first equation by 3, we're going to get pi over 18 plus 2 pi n over 3. And to make our next step go a little bit smoother, I'm going to rewrite this as pi over 18 plus 12n pi over 18. Now let's work on our second equation. Dividing by 3 is going to give us 5 pi over 18 plus 2n pi over 3. And again, we can convert this to 5 pi over 18 plus 12n pi over 18. These two equations give us all solutions of our original equation. So next what we have to do is use this information to figure out all the solutions on 0 to 2 pi. Now that we have all solutions to our original equation, if we want to narrow our view down to the interval 0 to 2 pi, what we're going to do is we're going to substitute in particular values of n until we reach 36 pi over 18. Now 36 pi over 18 is 2 pi, and this is our endpoint of our interval. So if our interval was from 0 to pi, I'd go until I reached 18 pi over 18. So how do we do this? Well, we know that all solutions are given as the following. First, I'm going to try using n is equal to 0. If n is equal to 0, this is going to be 0, and I'm going to be left with pi over 18. If this is equal to 0, then I'm going to have the solution 5 pi over 18. Okay, so here is for n is equal to 0. And we keep doing this until we get up to 36 pi over 18. Our next substitution is n is equal to 1, in which case we're going to get 1 pi over 18 plus 12 pi over 18 for 13 pi over 18. If n is equal to 1 over here, we have 12 plus 5 for 17 pi over 18. So next, let's try n is equal to 2. So here we would have 24 pi plus 1, which would be 25 pi over 18. Here, at n is equal to 2, we're going to have 24 pi plus 5 for 29 pi over 18. And we should be done here at n is equal to 2. That's because as soon as we substitute in n is equal to 3, we're going to get 36 pi over 18 for this part of our fraction, and then we're going to be adding more to it. So our solutions for n is equal to 3 are going to be larger than 36 pi over 18. So it looks like these 6 particular solutions are the full solution set for the interval 0 to 2 pi. To finish off the lesson, I want to take a look at 2 other common techniques that are used to solve trig equations. The first one we're going to take a look at is a factoring technique, and the second one we'll take a look at is utilizing a previous trigonometric identity that we know in order to help us reduce the equation to an instance where we're able to factor it. In this example, we're going to solve 2 times sine x times cos x is equal to cos x on the interval from 0 to pi. Now what you can notice here is that both of the terms on either side contain a cosine. So this indicates that factoring might be an appropriate way to go. What you don't want to do is you don't want to divide by cosine of x. We don't want to divide by cosine of x because there are certain values of x that make cosine of x equal to 0. So in some of those instances, we're going to actually be dividing by the number 0. What ends up happening is we end up losing some of our solutions if we do end up dividing by cosine of x. So instead, we're going to subtract cosine of x from both sides, and then we're going to factor out that common factor of cosine of x, and we're going to be left with 2 sine of x minus 1. Since we have the right-hand side equal to 0, and we have the left-hand side in factored form, this implies that either cosine of x is equal to 0, or 2 times sine of x minus 1 is equal to 0. Now I'm going to go ahead and solve the equation over on the right-hand side, and if we do that, we're going to get sine of x is equal to 1/2. So the goal on our next slide is to determine the x values that make cosine equal to 0, and to determine the x values that make sine equal to 1/2. So let's go ahead and solve each of these one by one. First, I'm going to begin with sine of x equals to 1/2 because we've already solved this in this lesson. So here we know that the value of x is going to be equal to pi by 6 and 5 pi by 6. This is on the interval from 0 to 2 pi. And of course, this is also acceptable on the interval 0 to pi as well. So if you do need to see where this solution comes from, just go back to the last example that we did. Next, let's focus on cosine of x is equal to 0. Now here, for me, it's easiest to use the unit circle. And remember that the cosine is the x-coordinate of terminal points on our unit circle. So we're kind of asking ourselves, when is the x-coordinate equal to 0 on our unit circle? That's going to be at two different points. There's a point here and a point here. This point is 0, 1, and this point here is 0, -1. And in both of these cases, the x-coordinate is equal to 0. Well, up top we have that x is going to equal to pi by 2. That's this angle measurement here. And then the one at the bottom is 3 pi by 2. However, we're going to exclude this particular value because this value is not on the interval 0 to pi. So, our final solution here on the interval 0 to pi, we have three solutions. Our first one is at pi by 6, our second one is at pi over 2, and our third one is at 5 pi by 6. In our last example, we're going to try to find all the solutions to the following equation. Sine of 2 times x is equal to sine of x. In this instance, since we know the double angle formula for the sine function, we can use that here to expand out this expression. So we can replace sine of 2x with 2 times sine of x times cosine of x. And now we're in a very similar situation to what we saw in the last example. I'm going to move the sine x over by subtracting sine x from both sides, and then I'm going to try to factor out that common factor of sine of x. Remember, what you don't want to do in this equation is divide both sides by sine of x, otherwise you're going to lose some of your possible solutions. Now, factoring out sine of x, we're going to be left with 2 cosine of x minus 1. So this means either sine of x is equal to 0, or 2 times cosine of x minus 1 is equal to 0. And we can simplify the right-hand side to cosine of x is equal to 1/2. So on our next slide, we'll work at solving both of these two equations. So let's focus our attention on solving each of these separately. Let's begin by working on sine of x is equal to 0. Here I'm going to quickly draw the unit circle, and remember that sine of x deals with the y-coordinates. So here we're looking for terminal points where our y-coordinates are equal to 0. And those are these 2 points here on our unit circle. So here I have 1, 0, and over here I have -1 and 0. Of course, my first one here is going to be 0 as well as 2 pi. And the point over here is going to be at a value of pi. Since we're going to be looking for all solutions of our original trig equation, it's going to be enough just to take one of these two values in our final solution. So I'm going to take 0 because it'll be the easiest to deal with, and then I'm going to take pi as well. Next, let's work on figuring out when cosine of x is equal to 1/2. So here we need cosine to be positive, so we're going to have two quadrants to deal with. And remember, cosine is adjacent over hypotenuse. So we're going to get diagrams that look like this, and this is going to be a 1, 2, √3 triangle, which means that our angle value is going to be 60 degrees, or pi by 3 radians. So we see that our first angle measure that we need is pi by 3, and then our second angle measure that we need is going to be all the way around here. This is going to be 6 pi by 3 minus pi by 3, or 5 pi by 3. Now that we have our 4 solutions on 0 to 2 pi, let's go ahead and find all of our solutions. First, let's work with 0. Since sine of x is 2 pi periodic, we're going to get the solution at 0 plus 2n pi, or just 2n pi. Next, again, since sine is 2 pi periodic, we're going to get the solution pi plus 2n pi. Next, since cosine is 2 pi periodic, we're going to get pi by 3 plus 2n pi. And finally, since cosine is 2 pi periodic, we're going to get 5 pi by 3 plus 2n pi. And of course, all of the n's here are integer values. So These four solutions give us all possible solutions to our original equation. All right, my little epsilons, stay positive.